If isotopes distributed themselves completely evenly or randomly among the different chemical compounds or phases in nature, they would be completely useless to study for a geochemist. Fortunately, this is not the case, and there is a lot of useful information and knowledge to be gained from analysis of isotopic composition in a material. The isotopic composition is often referred to as an isotopic fingerprint and can be used to identify a material or a sample, just as a fingerprint. But the isotopic composition will also be affected by the history of the sample. For example, due to chemical exchange of isotopes between the sample and nearby materials. Isotope analysis is important in geochemistry, of course, but also in a range of other fields, as you can see here. Isotope geochemistry can be divided into three different groups. We have the light stable isotopes, the heavy stable isotopes, as well as the radioactive or radiogenic isotopes. Applications and instrumentation differ slightly between the different types of isotopes. In this lecture, I will cover mostly light stable isotopes, but the basic concepts apply to all types of isotope analysis. We start at the beginning. What are isotopes? Isotopes are variants of a particular chemical element which differ in the number of neutrons in the atomic nuclei. For example, carbon-13 has 6 protons and 7 neutrons. That is a mass number of 13. The most common carbon isotope is carbon-12 that has 6 protons and 6 neutrons. A nuclide map shows us all the isotopes in the universe and can be seen as an expanded view of the periodic table. Isotopes are classified as stable if the half-life is very long, longer than we can measure. The majority of isotopes are seen to be unstable or radioactive and decays with half-lives covering a very broad range of different values. We should note that the mass given in the periodic table is an average atomic mass, weighted by the natural abundance of the different isotopes with their respective weights. If you are to analyze isotopes in the lab, it's helpful to know some details about atomic mass. First, we note that the proton and the neutron has very similar weights. The electron is very light. That means that an ion has a very similar mass to the atom. We also note that atoms that have the same mass number, called isobars, will have very similar masses, like argon-40 and calcium-40. The same is true for molecules. At mass number 28, we can have either nitrogen or carbon monoxide. This is very good to know when troubleshooting results from a mass spectrometer. We also note that the weight of an atom is not exactly the sum of its protons, neutrons, and electrons. This is due to the energy loss when the atom is formed from the separate particles through E equals mc squared. Isotopes have basically the same electron configuration, but differ in the number of neutrons, and therefore they have different mass. Isotopes of a certain element are chemically similar to each other because the electron configuration determines the majority of the chemical properties of an element. However, some differences exist, otherwise there would be no point in studying them. We call these differences for isotope effects. And some examples in the physical properties of water can be seen in this table. However, not only physical properties will differ. We also have subtle differences in the chemical properties. Especially the vibration of atoms within the molecule will be different due to the higher mass of heavier isotopes. This will affect the bond strength within the molecule and therefore the chemical reactivity. In general, heavier isotopes are less reactive than light isotopes. Isotope fractionation is the relative partitioning of the heavier and light isotopes between two coexisting phases in a natural system. Fractionation can occur due to the slower reaction rate of heavy isotopes, or due to slower diffusion rate due to higher mass, for example. But also chemical systems that are allowed to settle into a chemical equilibrium will likely be fractionated due to isotope effects on the chemical equilibrium constants. Some examples of fractionation that are relevant in stable isotope geochemistry can be seen here. For example, combustion reactions. If there is an incomplete combustion, we will always have some ash left, and that ash will be preferentially carbon-13 versus carbon-12. In phase changes, like evaporation, the heavy isotope will stay in the liquid phase. The same is true for gas-solvent equilibria, like carbon dioxide mixing in water. But it can also be more physical events like gas diffusion through a column or a septa. So in general, I would say that we should assume that every incomplete chemical action fractionates. And by incomplete, I mean that if a reaction, such as a combustion, is not perfectly completed, that is, that we don't have any ash at all, then we will get some fractionation. This means that we should follow the IT principle, the identical treatment of all samples and standards. Can we predict how high degree of fractionation we will get in a system? Well, there exists a number of rules of thumb. For example, the relative mass difference between the hydrogen isotopes is larger than for the carbon isotopes, resulting in a greater fractionation for hydrogen than for carbon. At low temperature, we have a small amount of kinetic energy available, which means that fractionation effects become large. So isotope fractionations tend to become zero at very high temperatures. There are also some rules of thumb when it comes to chemistry. So light or heavy isotopes prefer a certain type of chemical environment, like bond type or crystal structure, for example. Isotopic exchange will have a very small effect on the volume of solids and liquids, and fractionation will therefore be pressure dependent. However, this effect is in general very small. So the take-home message is that isotope effects are the most pronounced for light atoms or molecules at low temperature. There are unfortunately several ways of describing the degree of isotopic fractionation in a chemical system. All of these may be encountered in scientific papers. Consider an isotope exchange reaction. This is a type of reaction where the only thing that happens is that isotopes switch places. We can then define isotopic ratios as the number of heavy isotopes divided by the number of light isotopes in a certain chemical species. Note that isotopic ratios are always defined with a heavy isotope in the numerator. For the reaction as a whole, we can then define the fractionation factor alpha as the ratio of the isotopic ratios of the two chemical species in the reaction. For this reaction, alpha has a value of 1.012, which is larger than 1, meaning that oxygen 18 is enriched in liquid water as compared to water vapor. We should note the similarity between alpha and the definition of a chemical equilibrium constant called K. They are quite often identical to each other. However, the most common way to express isotopic composition in geochemistry is as delta values. We should note that delta values do not directly give the isotopic composition of the sample material. That is instead given by the isotopic ratio or sample. Instead, the delta values express the difference in isotopic composition of a material versus a standard. Delta values are expressed in per mil difference between the sample and the standard. So for example, if you have a carbonate, we can define the delta values for both the oxygen and the carbon. And we note that delta values can be positive or negative. If we have a positive delta value, that is the ratio of the isotopic ratios are larger than 1, that means that the sample is enriched in oxygen 18 versus the reference material. If you have a negative delta value, that means that the sample is depleted in the heavy isotope carbon-13. So why do we use delta notations? Well, we do that because it's technically very difficult to precisely measure the absolute isotopic ratio of a material. What we can do is to measure the difference versus another material if the two materials are measured at roughly the same time. So the use of delta notation and international reference materials increases accuracy and also facilitates inter-lab comparisons, which of course is needed for scientific papers. Here you can see some reasons why it's so difficult to measure the absolute isotopic ratio of a material. In the instrument, you have fluctuations in a lot of parameters in the instrument, and all of these will cause variations in the isotopic ratios you measure. You also have fractionation on an uncertain level, so the chemistry itself can also be a huge problem if you don't measure versus another standard at exactly the same time. This means that we need to include reference materials in every batch we analyze, and we also use reference gas pulses from gas bottles before and after we measure the isotopic ratio of the sample. Reference materials for stable isotope analysis is a very important field, so we have a lot of details about that. What you need to know is that we have primary reference materials that are international commercial standards that defines the delta scales. The R values of these standards are set to a fixed value. That is, they are not necessarily measured, but just fixed by consensus. We have secondary reference materials. These are more chemically diverse than the primary ones. Therefore, we can bridge the chemistry gap and have standards more similar to the samples. We also have the in-house reference materials that we use in the lab every day. And just note that we have a lot of requirements on the reference materials, so they should be chosen wisely. And the laboratory good practice should be that calibration should be performed using at least 2 standards, and they should have delta values that span a wide range that encompass the sample values. So when we report delta values, then we do that versus a reference material. For example, if we do a carbon-13 analysis of a sample, we report it versus the VPDB reference material with an isotopic ratio that has been determined by international agencies. We should note that for oxygen, we have actually 2 scales or reference materials that we can compare with. We have the VPDB scale that is used for carbonates, and we have the VSMO scale used for water and other types of oxygen-containing samples. These 2 scales for oxygen can be correlated to each other, and we can use this equation to convert one oxygen scale into the other scale. We note that the VSMO scale and reference materials stand for Vienna Standard Mean Ocean Water, which means that if we have a sample with 0 delta over 18 on that scale, we roughly have the mean ocean water isotopic ratio for oxygen. We'll now turn to the more technical aspects of measuring isotopic ratios. The most common way is to use a mass spectrometer. And we can simply say that a mass spectrometer separates ions according to their mass to charge ratio and quantifies the amount of each type of ion. We have 3 separate parts in the instrument. We have the ionization, followed by separation of these ions, as well as detection. There are different technical solutions for each of these 3 sections. The mass spectrometer cage is a gas isotopic ratio mass spectrometer. This type of instrument is primarily used for light and stable isotopes, carbon, nitrogen, oxygen, hydrogen, and sulfur. Samples can be solid, liquid, or gas, but solid and liquid samples must be converted into sample gases before they can enter the instrument. You can see what sample gases that can be accepted by the instrument here. In the past, it was common to do this conversion manually in the lab, but now it's more common to automate this process. We then use peripherals connected to the mass spectrometer. For example, carbon in a sample can be converted into CO2 by combustion in an elemental analyzer or by acid digestion in a gas bench. The sample gas will enter the instrument. It will be ionized by shooting electrons on the gases. The ions will then be separated in the magnetic field and then detected individually through different Faraday cups in the detectors. And this is how it looks like in real life. We have an elemental analyzer, we have a gas bench, and the mass spectrometer with the ion source, the magnet for separating the ions, as well as the detectors. The elemental analyzer is used for combustion of solid and liquid samples. For example, we use it for analyzing carbon and nitrogen in the organic part of sediments. We can run samples up to about 20 milligrams in size. Larger samples than that are difficult to combust properly, and then we get fractionation. The output will be delta values, but also elemental percentages. The gas bench is most commonly used for carbonates as well as for water samples. If you take it carbonate, like forams for example, and we then add some phosphoric acid on it, that acid will react with the carbonate, forming CO2. This CO2 can then be analyzed directly in the mass spectrometer. For water samples, we use a different technique where we have the sample water in a glass vial. We add some CO2 gas from a gas bottle. We will then get isotopic exchange from the water molecules to the CO2, so that the CO2 gas formed will have the isotopic composition of the water phase, and we can then measure delta O18 by measure the CO2 gas. Sample sizes required can be around 10 forams, but it differs, of course, depending on the size of the forams, and about 0.2 milliliters of water. The last thing I want to mention is an alternative technique for analyzing ratios of stable isotopes. Instead of using big and complex mass spectrometers, we can use lasers in a technique called cavity ring-down spectroscopy. These instruments utilize the fact that the vibration of molecules will be different for heavier isotopes. A laser pulse is injected into a cavity filled with a sample gas, and the light will bounce between the mirrors in the cavity until it is absorbed by the sample gas. The rate of absorption of a certain light frequency will be proportional to the isotopic composition of the sample. Picaro is the brand name most known for these type of instruments. I would say that the precision and accuracy is roughly on the same level as for a mass spectrometer, and it is a bit easier to take a Picaro into the field. Add-ons to the main Picaro instrument can give some flexibility, for example for analyzing carbonates, but still the mass spectrometer can analyze a broader variety of samples. And with that, we have learned the foundations of stable isotope analysis in geochemistry.